So we've actually been working static equilibrium problems since we first started working Newton's second law problems. But what we want to do now is see how this problem has changed now that we have objects in our problem that are extended objects. So when is a body in static equilibrium? Well, if your object can be treated as a point mass, then it's in static equilibrium whenever the sum of all the forces acting on the object add up to zero. This is known as translation equilibrium, and it's the first condition for equilibrium. Because this is a vector equation in a three-dimensional space, this would say that you've got the sum of the forces x equals 0, the sum of the forces in y equals 0, the sum of the forces in z equals 0. So whenever that's true and your object can be treated as a point mass, it's in static equilibrium. On the other hand, if your object must be treated as an extended object, well, now not only do you need to have translational equilibrium, where the sum of the forces add up to 0, giving us our x, y, and z component equations for the net force, but you also need rotational equilibrium, which tells you that the net torque acting on the object also equals 0. This is our second condition for equilibrium. We don't need to satisfy this second condition when our object is a point mass. So this only becomes an issue once we've let our objects be extended objects. Because this is a vector statement, you can say that the net torque about some pivot point in x equals 0. The net torque about some pivot point in y equals 0. The net torque about some pivot point in the z direction equals 0. Now, for this class, again, we're going to focus on problems that basically we can draw all the forces acting in the xy plane, which means that we'll have two force equations, or can have up to two force equations. And then because everything is going to be in the xy plane, the torques will all be into or out of that plane, which means we'll have a single torque equation. So for us with this class, given the fact that we're going to deal with systems that lie in a two-dimensional space, we're going to set up at most three equations for static equilibrium, even in situations where we have extended objects. So let's look at a couple examples here. So here's a situation where I have a box. It's hanging from two cables. So it's suspended from some ceiling by two cables. Because we can treat this box as a point mass, I can set up two equations that tell me that the sum of the forces in the x direction equals 0, the sum of the forces in the y direction equals 0. So what if we take that box, and now in this case, instead of suspending it from two cables, it's suspending from a cable, but that cable is attached to the end of a beam that hangs horizontally, and then is itself held up by a second cable. The box again can be treated as a point mass. So if I want to think about what's going on with the box, I could set up the sum of the forces in x and sum of the forces in y, and in this case there aren't any forces in x acting on the box. Unlike in our initial situation where the box had forces acting both in x and y, where the box is hanging from the end of the beam, there's really only the sum of the forces in y. For the beam, on the other hand, I can't treat the beam as a point mass. I care about the fact that this beam is an extended object. And so in this case, what that means is I'm going to set up three equations for the beam. So I'm going to set up the sum of the forces in the x direction acting on the beam equals 0. The sum of the forces in the y direction acting on the beam equals 0. The sum of the torques in the z direction about some pivot point equals 0. In this case for the box, we would set up two equations, both of them force equations, sum of the forces in x, sum of the forces in y. In this example, for the box, there's really just a single equation, sum of the forces in y. But the beam, because it has to be treated as an extended object, I have to care, if it's going to be in static equilibrium, not only do I need the forces to cancel out, but I also need the torques. So how is it that we're going to work a static equilibrium problem for extended objects? Well, we're going to work it basically the same way that we would work when we can treat things as point particles, with the additional difference of we now have to worry about torques. So I'm going to start by drawing an extended free body diagram. And again, notice the extended free body diagram here is going to let me see where all the forces act on my object. I'm going to pick a coordinate system, and one of the things that I'm going to care about is a pivot. And what we'll see is there are some choices we can make for pivots that make the math in the problem a little bit easier, and that's something that we'll talk about in class. 3, we're going to break the forces up into x and y components, and so we'll set up at most 2 sum of the forces equations. So again, there are situations where we might not need both of these because of what's going on with our system, but if we do, we'll set up 2. 5. So we want to calculate the magnitude and direction of the torque about our chosen pivot point for each force which acts on the object. And so what that's going to let us do, of course, is set up the net torque equation. And so sort of 5 and 6 are the additional steps here. What they're going to do is they're going to give us an additional equation. Additional equation almost certainly means additional unknown, and so then we're just going to have a set of unknowns that we go through and solve for what they are.